And I'm very pleased to give a quick introduction and then hand over to Dana Korf, who is the expert on standards and will elaborate on his works for the AME IPC standards. Dana, can you go to the next slide, please? So what is nanodimension? Nanodimension has the vision to change the world and change the way how we manufacture. We want to make a digital production possible. The company came from AME, additively manufactured electronics, and has involved now in additive electronics, surface mount technology, electronics manufacturing, and into additive manufacturing technologies. In the end, the vision is that in the future, we will not send parts around the world. We will send digital files around the world and produce them where they're needed on demand, anytime and anywhere. Next slide, please. So what are we doing today? On the left top, you see the systems for additive manufacturing and additive manufacturing electronics that we're having. The Dragonfly, the Fabrica, the Atmatec system. Below that, you see the materials, conductive and dielectric inks for electronics, ceramics, polymers, and metals. On the right top, you see our suites of additive electronics products, SMT products for specialized dispensing and pick-and-place solutions, and our digital printing platform from GIS, Global Inkjet Systems. On the bottom right, you see our software suite that has been expanded to Flight Hub and Control, a tool for digital manufacturing of electronics, and Additive Flow, a multi-material optimization and simulation software for AME, and volumetric manufacturing. And in the middle, you see the brain of it all, DeepCube, our deep learning engine that we are implementing in all our machines for optimized productivity and yield. Next slide, please. So what we plan to do is digital manufacturing. Digital manufacturing, and in particular today, additive manufacturing of electronics, where we build up layer by layer structures. That means dielectric material, which is a photopolymer, and conductive material, which is silver nanoink, are jetted simultaneously and then building up three-dimensional electronic structures. That could be a printed circuit board, a real printed circuit board, because it's built from the ground up in thousands of layers that are very different to the current layer definition that we have. And this process is much cleaner. The numbers here are coming from a UK-based consultancy firm. Of course, we can argue if it is really 94% less CO2 or 80 or 70, but it's significantly less. It doesn't use as water. We are not drilling, we are not etching, we are not electroplating. So we are having less waste, no water use, and less chemicals. But this new process brings also a lot of questions. Questions in particular for standardization and certification. Next slide, please. And so I want to hand over to Dana Korf, who spent his life in setting standards. And I'm very pleased that you are working with us and you're leading the next revolution in the AME. Thank you and welcome, Dana Korf.
Hey, thank you, Valentin. Excuse me. Yeah, my name's Dana Korf. I've been involved pretty much my entire career working on standardization, especially on new technologies. For me, having international standards is critical. One, so we have a common understanding, can develop materials and systems that are reliable, and we can learn from each other. So having to reinvent the wheel every time. So I got involved back in the late 70s when we were first doing high-speed digital design. And IPC had good standards for acceptability, but nothing about how to design for with transmission lines or crosstalk, et cetera. So we formed a committee and went on for several years to develop our first high speed. Then eventually for the microwave community, we call it high frequency standards out there. And not just for design guidelines, we had to develop also material specifications for the microwave community, because the standard FR4 material specs didn't really work well for PTFE and microwave type materials. So we developed that along the way with the design guidelines. So back in the late 70s, most board shops didn't know what impedance was, had never heard of a TDR. So I got a lot of phone calls saying, what's a TDR? What's 50 ohms mean? So during the 1990s, I worked, kind of moved on from the high speed work and started working on data formats. The data is a combination of Gerber files and a lot of, at that time, paper documents or fax documents. So we started working together, and rather than reinvent the wheel, around the beginning of the century, we formed a IPC project where we used the ODB++ XML version and the IPC Gen Camming. 4 years later, released the IPC 2581, which is the first global standard, single file, bi-directional standard for the printed circuit fab assembly and test environment. So along through this last 20 years, working on many committees. And a few years ago, we had decided we needed to create a digital twin standard. Obviously, handling data in the factory and feeding it back to design became important. So we formed a small group, and interesting enough, from the first time we met to the day we released the standard for publication, took less than 12 months. And we won an award for that, for the quickest IPC standard release. Typically, they take 3 to 5 years. So that was very impressive. And a couple of years ago, Nano Dimension contacted me saying, we have this new technology, AME, but there don't seem to be any standards out there. So that got me very interested in joining this effort to see how we could invent appropriate standards for the industry. So I was asked to chair this new, which I'll go into more detail, the AME D67 subcommittee. And out of that committee, various people from ASTM Additive Group asked if I would join their additive manufacturing electronics subcommittee to start seeing what they could do to support AME that's not in conflict with IPC. So I started, the first thing I want to look at is what is an AME part? When you take it off the machine, what is it? Well, it's a circuit board. So let's start with looking at IPC 6012 and 6013 for rigid and flex specs and seeing what we can use. So a small team of us put together our initial internal performance qualification kind of around the IPC 6012 format. And I'll go into more detail later on what's similar and what's different. But along when you have an acceptance spec, you need an inspection specification along the lines of A600. So we developed that document. And when you still look at 3D and the interconnect methods and the form components you can make in an AME structure, 2D Gerber-based coupons just don't make a whole lot of sense. The requirements do, but the coupons don't. So we started working on newly defined 3D coupons that we can use for qualification and performance. And along with these initial specs, I worked with many industry fabricators, CTOs, customers, potential customers in various industries to form the basis for these standards. So when you took our internal standard, looked at the global world, there's a lot of organizations involved in standards in the printed circuit board fabrication and assembly industry. So decided, well, rather than try and solve global hunger all at one time, let's focus on just a few key standard groups like IPC, UL, ANSI / ASTM along the way here. That's been our efforts, kind of work on the ones on the right side of the chart here initially, and then we'll expand out as required. The first document that got released, started late last year, got released in July, was from ANSI and the America Makes activity. And this document is basically an update of a 5-year-old additive manufacturing gap analysis. And so the way I got on the team, and we added in AME underneath the qualification certification as a gap. This is open for the public. Anyone can download it. There's no charge for this document. And then also I got involved in the data subsection. As one person asked me doing a sectional review one day, so why do we need electronics and additive manufacturing? I said, well, you start with a spring. We take that spring, we call it a coil, and hook up power to it. And the person kind of laughed, said, okay, now I understand. So this is out there already, which is basically a very good gap analysis. That some of it's being worked on, some of it isn't. Along with this, I've been working with UL, trying to understand how is UL handling additive manufacturing. And what they've done so far, on the right-hand side, there was what they call the blue card approval. This is I won't go into detail how UL works. It basically qualify materials and qualify factories that use those materials and document the process used to make them. And then obviously go through and qualify their acceptance, call it a certification test. So blue card, what they've done for plastics additive manufacturing is basically the factory is a machine. You have a material that's got UL approval. You have a process inside that machine to build a part, and that's their factory. So you can get a blue card approval just for plastic parts only. They currently don't have an approval for AME when you start mixing a dielectric and a conductor together, and want to make it into a circuit board. So what they've done over the summer, and it's not fully released yet, but it's past the voting stages, is updating the UL 796 to add in AME parts into the standards, saying our standards do apply for AME. Working a lot with Crystal Vanderpan on this. She's the expert within UL on circuit boards. We still have some work to do on coupons and some of the testing, but it's a good start. At least now we're part of UL, and people are required to have UL approval for their part. We'll now can get at least start the process to get UL approval, which is very important. As I mentioned earlier, as part of our IPC activity, the folks out of ASTM thought about, do we need any ASTM standards to support the AME technology? Don't really know what it is yet, but they're very, very interested in making sure we can synchronize and develop any kind of ASTM test methods, et cetera, to support this new AME technology. So I was invited to join the F42, which is the additive manufacturing group, underneath the application subsection, and apologize for the hierarchy here, but that's the way ASTM works. And they have a subgroup, which is 07.06, just looking at electronics applications. So I'm vice chair of that activity. And to date, there's been no new activities started, but we identified which group we would develop the standards or the test methods underneath. I think we're going to need a few either modified and or new test methods eventually, just based on what's out there today. So I'm going to dive into what we're doing in IPC. IEC folks, I met with them, we'll follow IPC unless we deem we need to do something different. So over the beginning of this year and into early summer, we worked with the IPC committee chair groups and decided that we would create an AME subcommittee underneath the D60 printed electronics group. There seemed to be a lot of close relationships with the people working on AME that are also in the print electronics industry. And I'll talk a little bit more about the similarities, the differences between PE printed circuit boards, which is interesting. We're really printed circuit boards. What we call printed circuit boards today are really etched circuit boards by our definition today. And so we were very fortunate to gather some experts out of various industries to initially start working on 3 standards. Let's see if I can get the laser pointer here. The first one, which I'm sharing along with Jeff Schubrooks out of Raytheon, is the IPC 6012 type. I'll go into more detail on each of these standards in a couple charts here. And then we were lucky to get Leo Lambert to volunteer to head up our acceptability committee. Leo is responsible for all the IPC acceptability for assembly and fabrication, standard 600, 610 groups. So very fortunate to get Leo involved with this. And then we got Tom Rivera out of Lockheed Martin agreed to assist us on developing the coupons to go along with these documents. We think these are the three important ones to start with. We had discussions whether to start with the design guidelines also, but we've kind of thought, well, we're not really far enough along yet with enough different suppliers to really start a design guideline. So we'll make notes what's applicable for the design guide as we work through our standards, and then launch that effort at a time that makes sense. Chris Jorgensen is our APC liaison. If you're involved with IPC, you probably know Chris. And we were very fortunate before the committee started. We had over 45, we're up over 50 volunteers from all over the world, competitors to Nano Dimension on the committee, some material suppliers, military, medical, consumer, Asian. We have two people from Japan and Sri Lanka on the committee, and obviously EU is heavily involved in this. And we have people from aerospace, both from European Space Administration and also suppliers to NASA are involved. So we have a very good group of people to start out with this. Again, the team members are coming both from the printed electronics industry and also from the printed circuit board industry. So it's a good team of people. We have a lot of expertise to start out with. Along with any standard, we'll start out, get our first revisions out, and you can see the numbers here that were signed by IPC. We're not sure where the coupon spec will fall yet, so it's just assigned an IPC-B, and we don't have a number for it, so I just put XX in there for now. We'll worry about the actual document number later on. Okay, with IPC, one nice thing they've developed over the years is what's called a team. Basically, you take a small group of people out of each of the committees, you meet bi-weekly, and you focus on creating a draft of the new standard. And then the goal is to get it out to the general committee as fast as you can, and then have everyone start going through line by line, word by word, to create very good, very fair, and valid standards that can be validated in the industry. Name the team Chaos. This is Danish for chaos, believe it or not. You have to pick unique names with some humor in them for 18 names. We started meeting last month. We've been meeting bi-weekly with a small group of people. We're going through the draft that Nano Dimension donated. We actually donated our internal specs to IPC, so we wouldn't start with a white piece of paper. Start with that and start going through and modifying it to reflect what the industry wants. So our A team, you don't want to have an army of 100 people because it goes very slow. So we started out working on the performance spec first, and we have 12 industry volunteers working on this every other week. We meet on the phone and start going through section by section. It's very working on standards is from an engineer standpoint is can be very boring because you're looking at what does the word "the" mean and when we use this or that, but how you get to a very good verifiable standard. And so we discussed about the A team when we set the team up. We said, well, we'll note what kind of coupons we might need and what kind of acceptability pictures we're going to need as we go through the document to update what we did in Nano Dimension. And then once we get through the 6905, which our target is by February of next year, we'll get our goal is to have a draft document ready so that the IPC Apex meeting in April in the Los Angeles area, we can get the committee together and start going through the extensive review. The IPC standard schedule for standards is 5 years. Hopefully we can do this in a couple of years. It'll be great to do it within 1 year, but this is a brand new effort, and this might take a little bit more time. So one area we look at the standards and how we call stuff and what we name it. I put this together a chart. I've used this a few times. Is what's the difference between a print electronic substrate and an additive manufactured substrate? And if you use the IPC and ASTM definitions, here's their high level descriptions of the processes that are used. And The way I kind of fundamentally look at this is inkjet printing and material jetting are fundamentally the same thing, but used in dramatically different ways. So we also have a term which everyone uses, is called 3D printing. That gets overlapped for both processing techniques. So our goal in developing this standard is to create one standard that's process agnostic. In other words, it doesn't matter how you create that AME part, which additive manufacturing technique you're using, what type of machine, what type of materials, but the requirements should all be the same regardless how you get there. A lot of the ASTM specifications and IEC specifications are around the exact method of manufacturing for additive manufacturing, both for plastics and metals. So there's a lot of detailed specs defining what you need to do to make the part and how you document the results. We're going to try and stick to as much as we can. Just make it doesn't matter how you get there. What are the requirements when you take the part off the machine? And even what do we call it? Do we call it a part, a substrate, a board? We still have to work on what are we going to call this thing that we've invented. It fits all sorts of different categories, which makes this intriguing. And those of you on the call today that are already in, you have AME machines or looking at it, realize that we can create rigid flex and rigid flex on the same machine at the same time. We create rigid flex part, a rigid and a flex board in different parts with the same materials at the same time. So the goal will be here to hopefully we can combine the rigid flex and rigid flex into one document, one set of requirements, versus the IPC method where they have a flex and rigid separated in the two different paths, and the rigid flex is part of the flex. I think because in a factory, you have different factories that build the parts. You may have a rigid factory that builds a rigid portion of the flex and then send it over to the flex factory, et cetera. In this case, it's all in the same machine. So it's a different way of thinking about the standards and requirements. How do we define AME? We have a proposed definition we got in committee last month. We'll submit it out to the general committee next year to try and work on what is an AME part versus a PE part versus true additive manufacturing. I like the ASTM definition because it is cited as the method of joining materials from 3D model data, in which layer upon layer versus subtracting material is how you form the part. That's a very clean definition for additive. So what do we need to add in or modify to get the electronic functionality into the AME definition? Our initial proposal up front versus having 6 different printed circuit board categories that 6012 and 2021 series standards have, I think we're going to try and do 2 basic types. One is we have a circuit board with 3D formed components inside. So in other words, you're forming inductors, antennas, resistors, whatever, using the materials that you're printing. And then the second type would be when you start to embed components into the substrate, either unpackaged and or packaged components. So we're kind of let's kind of keep it simple. These two standards, and in the embedded part, we'll try to use or just modify slightly the existing embedded standards through IPC, not have to invent a whole new standard. I think we can do that. Just working with that committee and looking at their standards. Okay, so this is just a doc. I gotta move a window down here so I can see. There you go. So we're taking right now fundamentally the requirements out of the 6012 rigid, 6017 HDI, and the 6013 flex, and kind of creating our first document, which is called 6905, is the number that's been assigned to it. And we're right now only working on the form components. We're not going to worry about incorporating embedded at this point for this initial draft. We may adopt it when we go through full committee review, but right now we decided to just kind of keep it simple and just work on the form component version of the spec. The effort we did with the nano dimension have a pretty good cut of what the requirements are. So I call it, we started out with probably an 80% complete standard from a requirement standpoint. And then we'll see what we need to add, delete, and modify as we go through the document. Sorry. So what's the differences between our, from a IPC spec standpoint, 6012 as the basis, and an AME circuit board? So if you go through the document, 6012, we went through initially, you start looking at, well, there's specifications of 6012 using manufacturing techniques and materials we don't use. So you just start taking them out. I have a lot of years background in PCB manufacturing and front-end tooling for boards. So I indicated on this in the next chart, which areas are kind of the top 5 defects, generally speaking, in any board shop when you actually build a circuit board. We don't start out with copper foil or cores or reinforced cores or prepreg, so we took out all those requirements. We don't laminate. Right now, no one puts on secondary surface finishes in the machine. That might change in the future, so we took out the surface finish requirements. There's no copper plating, no copper etching. We don't need VIPO, plated over filled holes. We just, you just build it up as you need it. We don't need laser drilling. We don't need back drilling. If you don't want material there, don't put it there. It's a really interesting concept. And there's a lot of requirements around plating and materials in the IPC specs, because that's where a lot of the impacts on reliability and yield occur. We don't need a secondary solder mask or via fill or legend. You just use the same dielectric that you're printing for the dielectric for the between the conductors. Drilling, don't have to worry about drilling or drill miss registration, because you're not taking an existing board and trying to guess where the pads are to align the drill bit to. And right now, no one's really using internal metal cores, which is a fairly minor point in 6905. So if you look at it, around half of the defect categories that are in traditional boards just disappear because we don't do them, don't need to. But what's different? With anything, there's always something, nothing ever comes for free. So when you're doing a print layer by layer, we have to be honest with ourselves and look about what could go wrong. Doesn't mean it will, but what could go wrong, and what test methods do we need to validate that it's okay, and what's an acceptable criteria. I had one military person in a meeting one time suggest that voids. He goes, we've had voids forever, but if a void doesn't create an open, why do we care? And so maybe we need to relook at even basic things like void formation or what's left over as a void. It's very interesting. As you know, we print a silver conductor, and it's sintered. So the cross section and the surface of it is much different than when you take a copper foil layer, etch it down or plating onto it. So what's different? What could go wrong? You got to look in standards as what could go wrong, and how can we prove that the end product is okay? Handling damage, I indicated here, a top 5 defect, because it's generally speaking, the entire process is in a machine. You don't have to take the boards out or handle the devices between operations and walk around factories and carts and go between buildings or cross streets or on trucks and stuff. So you have a lot less handling damage. So we can remove some of the requirements that you would have in a traditional board, but we have to think about, well, maybe someone will take the part out when it's partially created, do something, put it back in again. So we're going to have to figure out what could go wrong in a full additive environment. And one thing that's really interesting in the AME world is low temperature soldering, low temperature stresses. Right now, the parts are relatively small. You don't need to have 260C reflow, but you do need to put it onto a board that has 260C reflow. There's also the ability to do adhesive bonding, which is not really covered in any of the IPC specs at this point. So we're thinking of adding in and allowing adhesive bonding within the board and to the board. And that would be a whole new area for IPC for both bonding parts and also bonding sections of the board if you need to. We don't have just flat XY copper traces with a vertical hole being drilled through. Our holes can go in different angles. They might be solid, they might be star-shaped. Who knows what the shape of the hole will be? And we can create, the concept of a wall versus just having a plane horizontally in the board. You can have a wall going vertical or on an angle. So what could go bad with that? Don't know yet. So we may need to develop a specific test method and coupons in particular on how to test different form factors and interconnect methods. And then roughness is an area we have. You can have a conductor to dielectric or conductor to conductor roughness specs that you don't traditionally have in an etch board. Typically, you just have a surface roughness based on initial material roughness or the processing that goes through. So, and then cleanliness, of course, you want to make sure you have some cleanliness specs and a method to measure it. So these are some new areas that we have to add into the document that are different than rigid boards. And we'll need to develop, we developed some guidelines within a nano dimension, and we'll probably come up with other areas that we haven't thought about yet, which is the power of having a good team involved in this. So right now, the IPC standard is 6905 is focused just on rigid. Well, I'll put a note here. When you do a comparison of 6012 and 6013 and the related documents on what is actually different between a rigid spec and the flex spec and the flex/rigid flex spec. And when you actually compare, it's really only 5 different areas. One is, well, we have different categories, obviously. And then you have the flexible zone, which is different than the rigid zone. That can't make sense. Rigid boards aren't supposed to bend. Flexible ones are supposed to bend. So there's different requirements there. The interface between the flex and the rigid area, there's lots of work in that area because that's where a lot of damage can occur for a whole host of reasons. I won't go into them. So that actual interface has to be defined. And then how you lay out parts, how you route traces across the transition zone is much different than it is when it's just a straight rigid design. And then obviously, how do you bend it? How far do you bend it? How many times can you bend it? Is very applicable for flex versus rigid. So bottom line is, if you look at flex versus the rigid, there's not many requirements. So there's a possibility we may want to add the flex/rigid flex into the rigid document as when we go to general committee. We may elect to leave it out just to keep it simple, but we'll see what happens. There's really not much different here. So I thought I'd just put a note in here that for the back of our heads is we have a chance to combine them and not create a whole new suite of standards and, kind of keep this simple. Okay, coupons, these are showed on this table here. This is an internal table I use. Here's a standard 2221 coupon definitions I use in the industry. I created on here. I've never liked, this is just a personal thing. I've never liked the ABPG. I don't know what that means. I worked in Asia for 8 years, in China for 8 years, and what's a G coupon in Chinese? So one idea I've thrown out for discussion. This is not approved. This is not even, we're not even talking about coupons yet. Possibly let's rename them with something that makes some sense. Has a abbreviation makes some sense. So these are coupons that I believe will do the same functional analysis, maybe in a different way. Solder mask is an interesting area where solder mask, if you use the same dielectric as your mask, you don't have requirements of testing around putting another type of material on top of another material. Registration is almost non-existent because you can print next to the pad. You don't have to worry about registration openings, but the outer layer has to perform as a solder mask. Another thing, this is a really interesting area in mask, is on traditional PCB specs, you have a top, you have a bottom, and you have sides. Well, in the AME world, you have surfaces. Okay, you may not have a traditional edge like we have in IPC, like on traditional rigid boards, but you might have an edge if you're doing panelization, array panelization. So how do we look at some of these things like surface finish, solder mask, etc., solderability when it's not a flat surface and it may be on the sides? We need to address that. I'm not going to talk about possibilities here, but that's an area that's a little bit different. And then the traditional impedance coupons assume you have a strip line or microstrip line in your circuit board. Well, now we have embedded coaxes, we have embedded twisted pairs, we have waveguides, we have antennas. We have several different form factors of actual transmission lines or timing or loss sensitive distribution methods. So we might need to add coupons for different form factors. It may not be possible to create coupons for all the different methods that are being developed, but I threw a couple extra ones in here just to start the thought process of what we may need to do. Also, creating a Gerber file based coupons doesn't make any sense in a 3D world. Gerber's for 2D. So we might need to use AMF, 3MF, STL, or maybe a new standard format for these files, and move on from the 2D Gerber formats. We need to figure out from an IPC standpoint what file format we want to use, because some of these are proprietary, some of them aren't. And in the additive world, there's a lot of discussion what's going on and how do we get to more modern, more comprehensive, just additive manufacturing file formats like AMF or 3MF. So we might be able to create less coupons to do more testing at one time. Don't know. We might need to have more sections than we do for PE. So coupons is a big area. To me, this is the hardest one to do so far, because it's so much different than a flat board, which has 80 years of experience or 70 years of experience behind it. Sorry, click back here. Acceptability. This is an area we need to look at. I put this one in here on purpose. Acceptability criteria says for whatever the requirements are in your performance acceptability standard, here's the visual pictures along with the requirements from the standard on what's good and what's bad. So I put this one in here because this is an interesting one here where I have a little piece of silver sticking out of my via hole. That in a rigid board would be bad. That'd be a fail. But this one may solder back. It's non-functional. It doesn't hit a pin going into it. But if it's left alone, it might vibrate out, fall off, and go affect another circuit. So we need to look at the final results of a AME circuit and decide, are these, we may need to have different pictures and different requirements because just the way it's made. So I put this picture in here on purpose. Our approach is on the 6911 document is take the A600 as a basis, modify just like we did the 6012 document, subtract sections that don't make sense, add sections that do. And Leo and his team will go off and review that. I mean, closing here, we're not looking at a data format yet, but I put this in here because data is very, very important to me. In the board industry, we have a significant amount of errors just transferring data from a designer to manufacturing because they use Gerber-based formats. We have lots of different files that go together that contradict each other or have errors in them. Like the net list has a fundamental error in it right now, the 356 net list at 2581 resolved. So as we go forward here, and this is a multi-year effort, what's going to take, and again, there's no real hard project going on yet, but started talking to various groups on how can we take the electrical and the assembly functionality from maybe a 2581 or an ODB++. ODB++ is owned by Siemens now. This is the only industry standard in the market right now for circuit boards. And take a look at one of the 3D formats that are out there, or maybe two of them. How can we merge the 3D component of AME in with the electrical standards out there? And how can we come up with a bi-directional format for AME? We're working right now with the ASTM ISO 261 Group 64 with their AMF document, working with the 3MF consortium and trying to figure out, can we come up with something before AME gets in a high volume with hundreds of vendors? If we can get this decided early on, we cannot replicate the issues we're having on the rigid and the flex circuit board on transferring data back and forth. So I put this in here this is something to put in the back of your head. We're going to need to work on eventually in a more formal format, but this is pretty new to everyone right now. This is identified as a gap in the American Makes section. So kind of closing here, we'd like to have more people participate in the standards development. The more, the merrier, as we say, and also the better specification we get at the end of the day. You need lots of different people looking at it from their different perspectives and trying to shoot holes at it. Say, what if we do this? What if we do that? Or what if this happens? Or we need to look at class 1, 2, and 3 type of environments. Class 1 basically in the world is not used anywhere, though it's defined really as a prototype or proof of concept type of level. So maybe we resurrect Class 1 again and use it in the AME world. So if you'd like to join, please contact Chris Jorgensen. We'd be happy to add you on to any of the task groups, the A team, if you wanted to participate in a more detailed approach in the short term. And maybe you have other ideas on standards that we need to have or are missing. So thank you for your attention, and I'll turn it back over to Natalie for questions.